once the midterm is graded, there would be more details about that. So part of it is that how you grade the midterm is kind of also a way of adjusting things, right? So you could be more or less lenient when grading. So, okay. So what I want to do today is I want to go back to the memory model. And I know it's Friday, but I got to do it. So on week 7, please go to the memory model worksheet. So this is this, and this is this link. And what I'll ask you to do is to just kind of, for each table, to just do the exercise. So fill in the globals and the locals and fill in the memory table. So you might want to do it kind of on a computer, or you could do it on a piece of paper, doesn't really matter. So I think we'll start with exercise A. And I'll give you kind of, let's say 5 minutes to kind of try and discuss it and try to figure out what's in there. Go ahead. So again, if you go to week 7 memory model worksheet. Okay, all right. So most people are, for one reason or another, not doing the worksheet. So I'll I guess there's other things. So I'll first do this guy. So so this is the function. So let's kind of do the memory model, and then we'll also do kind of the more intuitive thing. So we'll have the memory table, and in the worksheet it's 1040 and so on. So this is going to be address, and the value is going to be here. So 1000, 1040, 1080. All right, and then we have the variable table. So we have two variable tables, right? So one is for the global. So here the M is global, and there is also a local M. So this would be the global one. And we'll also have a variable table that's local to F. So M equals 5. So 5 needs to be somewhere in the memory table. So for example, here. And now we're saying F of M. So here M is going to be at 1000. And we're saying F of M. So what does this mean? So this means that this M gets sent to the N here, right? So it's as if we're saying local N is equal to global M. So what does that mean? It means that we just take this guy and we just copy it over here. So this is also 1000. And this is N. And the process is this gets copied here. Now, in the case of integers, it's not a very interesting fact. It's just that now N is 1000 and also M is 1000. So both are 5. So now we're saying M is 6. So this M, we didn't say global M. So that means that this M is a local variable. So that means that it goes in the variable table. The right-hand side is something new. So it needs to be somewhere in the memory table now. So for example, here. And now we're saying M is equal to 6. So that means that this 1040 goes in the local variable table for F, like so. And now we're saying local N is equal to local M. So anytime you have an assignment where on the left-hand side it's just a variable, what happens is you just copy from here to here. So 1040 goes here as well. So note that in this process, like it's obvious that if you're assigned to a local variable here, this cannot have any implications for anything outside the function. And that's because what happens is this address gets copied here. That's it. The global M doesn't care at all. It's still 1000. So this means that when we get back to print M, this is gone, M is still 5. So the intuition here is, this is kind of people's usual intuition, is you do something with local variables, it doesn't matter for the global. And this applies when what you're doing is you're just assigning to local variables. So where this intuition breaks is if you were to, so this is the end of exercise 8. So where this breaks is if you go and you have a function like this, and you say something L at 0 is equal to 5, and then here you're saying L is 1, 2, 3, and then you're saying G of L. Over here, it would be true that L at 0 is now 5. And that is because what you're doing here is you're not changing the local variable table. You're saying go to L at 0, so go to a location in the list L and change the content in that location. Some people incorrectly think that this means that lists are different from integers, they just behave differently. Not the case. They behave exactly like integers. It's just that if you're saying L at 0 equals 5, you're doing something that's not possible with integers, right? So the equivalent with integers would be like go and multiply a digit in the integer. Not what we're doing here, right? So if you treat the list as if it were an integer, so if you were to say something like L is equal now to the list 7, 8, 9, that does not affect anything outside the function. And that's because if you're doing something like this, that's equivalent to doing something like this. Right? You're just saying, I have a local variable L, and now I want it to be something different. That places this something different into the memory table. And it makes the local L be this something new, but it doesn't affect anything outside the function. On the other hand, this has an effect outside the function because this is saying go to the memory table where L at 0 is and multiply L at 0. And if this L and this L are aliases, which they are because you send this L here, then yes, that would have an effect outside the function. All right, so with that in mind, let's do exercise 2B. So that's kind of the same idea, right? So I'll give you a couple minutes to just do exercise B with what I said in mind. How many people have done exercise B? All right, so chill for a couple minutes or do exercise C, which is usually the challenging one. Everyone else, let's try to do exercise B. All right. So let's think about B. So B is really the same as what I had discussed just now. So what do we have? So here again, I'll do the memory table and the variable table. So here we're saying L at 1 is equal, L is 6, 7. So that means that in the memory table, we need to first place 6 and 7, and then place the rest. So for example, 6 would go here, and then 7 would go here, and now we're able to put the 6, 7 in the memory table. So this would be at 1000 at 1040. And now we're able to place L in the variable table. So this would be at 1080. So now we're saying f of L. So what this does is it sends this L to the local L. So we'll have a local variable table as well. And the local variable table would say, okay, so L is also 1080. And that's because this just gets copied over here. Now we're saying L at 1 is equal to 6. So L at 1 means go to the list at 1080 and make it 6. So this one becomes 1000. Make sense? So now we're saying L is equal to 5, 6. So what we got to do is we got to put 5, 6 in memory, always like a new thing on the right, put it in memory, and then assign it to the local L. So that means that we got to place 5 over here. And now we have a new list that's 5, 6. So that would be at 1120, at 1000. And now the local L would be this new thing, 1160. And that, of course, does not affect anything outside, because what happened is we made a new list, and then we said the local L is this new list. Don't care. So now if you print L, it would be the old L, 6, so 6, 6. Yes. So you mean if you say like, you're asking about this stuff. So so the answer is actually neither. So I'll do that like actually right now. Yes. So global L here, you cannot say because L is a parameter. So that would be just a syntax error. So if you have something like global L1 and then you have an L1 here, I think that's kind of the thing that you're asking. So nothing becomes alias unless you directly assign. So the only things you could do is you could say, L1 is, so are you asking like, if I don't have, so if I start saying like not global L1, but like L1 equals to this, and then there's also a global L1? The answer is no. So this L1 is a local variable and this L1 is the global variable. They're separate. Yeah. Yeah. And that like it happened before. It's like this is basically this one. Yeah. Can you modify global L within the function? The answer is it's kind of complicated. So because you have this, sorry, guys, I mean, this might be on the exams. So yeah, like we are having a chat and it is like 10 minutes before the end of the lecture, but still. So the answer is here you have L as a parameter. A parameter must be local. So your question is, well, can I access the global L since I have the local parameter? Yeah, I mean, totally. Like you can say L at 0 equals 7, that modifies the local L. So if you're inside the function and you have a local variable named L, when you're referring to the local variable named L, that's the local one. So this so like if you just say L is something new, now L is something new. It's as if you had said like def G and it takes N, and then you say like N is equal to 6, but you code it with 5. Well, N used to be 5 and now it's 6. In the same way, L used to be something and now it's something new. Well, sorry, guys. Everyone, give me 10 more minutes, please. Quiet down, please. gamma 06 actually. 07, sorry. Oh, 03. Okay, the gamma 07 is what? Okay. All right. So the question was, how come when you say L equals 5,6, that doesn't affect the L outside? And the answer is, well, it's the same as this. So why is it that when you say N equals 6, that doesn't affect the value of 5? Well, that wouldn't make sense. 5 is 5. So in the same way, here, like L is L, and then in the local function, you're saying L is something new. Okay, L is something new. That's the local L. In the same way, here you're saying N is something new. Well, that's the local N. It's not, obviously, it's not 5. And the reason this is kind of, I think, a good example is because it shows the intuition. Like, obviously, you cannot change the value of 5. In the same way, like, obviously, you cannot change the value of L. So the difference is with integers, there is a way, if you go to the footnotes in the memory model handout, there is a way to modify the contents, but in Python in general, you do not modify the contents of an integer. You can go inside the contents of a list in memory and say L0 is something new. All right, so that's the difference between integers and lists, is they're treated the same way. It's just that you can modify the contents of the list. Make sense? So, okay. So there was a question about placing 6, 7, 5 and stuff like that. So I think that's what we'll do for the next couple minutes. So placement of objects in memory. So in some ways, this is kind of like details that are maybe not super important, but at the same time, I think since we're doing it, might as well know this. So here's what happens if you do something like this. So I'll say for I in range -10 and then 256. And I'll print ID of I. So I print where it is that -10 is placed, where is -256 placed, and so on. And what you see is this kind of interesting pattern, right? So the pattern is you start with like very large addresses and they're not consecutive. And then starting with -5, the addresses become consecutive with gaps of 32. So the reason is Python 3, and that's dependent on which Python you're using, but specifically CPython 3 places -5 up to 255 in memory before running the program. So anytime in your program that you say something like A is equal to 5, actually 5 is preloaded. So Python will just look up where 5 lives in those addresses. It's going to be different on your computer, but it's always going to be preloaded. And anytime you say 5, it's just going to look up where 5 lives. This is specific to -5 to 255. Something like -10. If you say ID of -10, what happens is, well, -10 has got to be placed in memory. So in my case, -10 got placed in that address. And then Python will just say, okay, like that's where I put -5. Here's something interesting. You'll notice that this address and this address are the same. So the address of -10 is the same as the address of -8. The reason for this the reason for this is that -10, once I becomes -8, -10 is not accessible with any variable that's currently in the program, right? So when I is -8, there is no variable that refers to -10. In fact, that's true with -9 as well, right? And that means that, so the address where -10 used to live can be recycled to store -8. Right? And that's because like I is -10, okay, we got to store that, but then I is -9, and then I is -8, and at that point, you don't need a variable that will store -10. So why is it that -9 it doesn't get placed in the cell for -10? Anyone? Yeah. Say again?
For -9, it's -7.
That's right. Yeah. So why is it that for -9 it didn't get the type?
I guess it's when you want to.
No, that's not it. Anyone? I mean, empirically, that's what happens, but that's not why. So what's going on? Actually, like it actually makes sense if you think about it. So imagine that you're saying like I is -10, and then you're saying I is -9. So until I became -9, I was -10. So you first need to place -9 in memory, and only then do you get to say I is now this. But when you're placing -9 in memory, I still refers to -10. Yeah, right. Empirically, yes. But why? Well, because when you're placing -9 in memory, I still refers to -10, so you cannot recycle that. The first -9 gets placed in memory. You put that down, and then -10 gets placed in memory. Yeah.
You use like I-1 or I-2 in the, does it still maintain the value of?
So if you use something like I-1, well, both I needs to be stored and I-1 then gets placed in memory, and then you can print the ID of it. Yeah. 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 So that would depend on the exact implementation of Python. It's not defined. So if you say A is -9 like this, then, and you printed the ID of A. So the reason I'm trying is I'm not sure. So you go to -5. So here, this is like this, and that turns out to not be recycled at all. And that's because it doesn't know that I'm not going to use A. In fact, I can still use A over here. But that's because I'm in the interactive environment, in principle, it should know that I'm not going to refer to it, and that is the recycle. Yeah. All right, so that's that. I feel like I'm trying your patience. So I'll end with this, and we'll start afresh on Monday with exercise T. I'll see you. Bye.